All right, so Doppler effect equation, frequency heard by the observer is the frequency created by the source modified by this ratio of speeds. So let's try an example. Let's say there is a car that's creating sound. Maybe there's a speaker mounted on the top. And this is creating a sound wave. So the sound is spreading outwards in all directions. And let's say we know the frequency is producing. Let's say the frequency is producing, frequency of the source is, let's say 500 hertz. And let's say you're standing over here and you're listening to it. If nobody's moving, if you're standing still and the car is standing still, what frequency would you hear?
500 hertz?
Yeah, you would expect to hear the same source. If nobody's moving, if the source is staying still and the listener is staying still, you're going to hear the same frequency that the car is producing. And let's check if that matches up in the equation. If you plug in 0 for speed of the observer and 0 for speed of the source, these are gone. What's speed of sound over speed of sound?
1.
Yeah, V over itself is just going to be 1. So we get the frequency produced by the source times 1 is the frequency heard by the observer. So this Doppler effect, in this simplified case where nothing's moving, the Doppler equation still predicts what we should expect. It predicts exactly that, that the listener is going to hear exactly the sound that's being produced. But now let's take a look at what happens if somebody's moving. Like, let's say, for instance, the car is staying still, the source is staying still, but the listener is moving. Maybe you don't like this sound, so you are running away from the car. So you are moving away from the car with a speed of, let's say you're running at, let's say, 8 meters per second. So that would be the speed of the source. If you're running at 8 meters per second while the car creating the sound is staying still, would you expect to hear a higher or lower frequency?
Lower?
And why is that?
Because you're running away from the source of the sound, so it would emit a lower frequency for you?
Yeah, lower frequency in the sense of, what do we mean by frequency here? If you're moving and the source is staying still, the crests aren't really changing how far apart they are. The crests are moving out from the car. The crests are still spaced the same distance apart. But how do we define frequency? When we say the frequency is like 500 hertz, what does that mean? In terms of what you actually hear, yeah, it determines the pitch. Higher frequency means you hear a higher pitched note. Lower frequency means you hear a lower pitched note. But what is it? What's the physical meaning of frequency? If we say the frequency is 500 hertz, what's the speaker actually doing? What does that tell us about the wave it's creating?
Isn't it the number of cycles per second?
Exactly. Frequency, 500 hertz means 500 cycles per second. Hertz literally just means things per second, things happening per second. So the speaker is vibrating 500 times per second and creating 500 outgoing crests per second and 500 outgoing troughs per second. So when the speaker is producing a 500 hertz note, it's creating 500 wavefronts per second. If you hear 500 hertz, that means you're receiving 500 wavefronts hitting your eardrums per second. But if you're running away, one wavefront hits you, but then you run a little distance. The next wavefront approaching has to go a little bit further because you've moved away. Move away further, the next wavefront has to go even further. So each subsequent wavefront takes a little bit longer to catch up because you're moving away. Each wavefront has to travel a little further than the previous one did. So that means you're spreading out the waves in time. You're not being hit by as many waves per second as the speaker is producing. So that causes a lower frequency. So conceptually, we should expect a lower frequency heard than the frequency being produced. And let's see if we can calculate exactly how much lower. If we actually write out that Doppler equation, and of this, what are we trying to calculate here?
The speed of the observer this time, because the source is stationary.
Yeah, in this case, let's list out what we know. We know that the speed of the source is 0, because in this case, the speaker is not moving. What do we know about the motion of the listener?
It's 8 meters per second.
Yeah, in this case, we know the speed of the observer, 8 meters per second. So we know speed of the observer, we know speed of the source. Do we have speed of sound?
We could do it by v equals maybe the wavelength times frequency, maybe? No.
If we knew both of those, yes. In this case, we know the frequency, but we don't have the wavelength. But since this is sound and nothing else is specified, we can probably use just the standard value for speed of sound in air. Typically and realistically, this should be given in a problem. But if it's not given, I would usually just assume that speed of sound in air is about 343 meters per second. That's the usual standard value for speed of sound in air at standard temperature and pressure. I think it's specifically at 0 degrees Celsius and one atmosphere of pressure. So that's going to vary to some extent based on temperature, but 343 meters per second is a good standard value for speed of sound. Maybe a little faster or a little slower. Sometimes we round it off to 340 or 350 to simplify the calculations. So we've got the observer, we've got the source, we're using the standard value for speed of sound, and we also know the frequency the source is producing.
In the equation, is v usually the speed of sound? Like all the time?
The v here, the unlabeled v, is always the speed of the wave you're talking about. So if you're talking about a sound wave, you'd use speed of sound. If you're talking about ripples in a pond, you'd use whatever speed those ripples spread out through the water. Or if you're talking about light or radio waves, you'd be using speed of light. And radio waves, by the way, are just a form of light beyond the visible spectrum. Radio waves, microwaves, X-rays, gamma rays, and visible light, infrared, ultraviolet, those are all just different wavelengths of light. So they'll all be traveling with speed c, about 300 million meters per second. But for sound, the speed is about 343 meters per second. And again, that would usually be given for whatever type of wave is being discussed. But typically for sound in air, the speed will be about 343 meters per second. For light, any form of light, the speed is 300 million meters per second. That's usually just written as c, the speed of light, and that's 300 million, or 3 times 10 to the 8th meters per second. And that's true whether it's visible light or anything beyond the visible spectrum, such as radio waves. Sound, on the other hand, is typically about 343 meters per second. In air, anyway. It's going to be faster in liquids and even faster still in solids. But in sound in air, about 343 meters per second. And then it looks like the only unknown left is frequency heard by the observer. And we can now use the Doppler effect equation to calculate that just by plugging in all these numbers. So writing that out as the equation and filling in the values we know, frequency heard by the observer should be frequency created by the source, 500 hertz, multiplied by speed of sound plus or minus speed of the observer. And speed of the observer here is 8 meters per second. We're going to have to be careful about positive or negative, though. We are expecting a lower frequency. So should we be using plus or minus here?
Minus?
Yeah, we should use minus, because if we want the result to be lower, if you're multiplying by something and you want the result to be lower, we want a smaller numerator or a larger denominator. So to make the result smaller, we want a smaller numerator, so we'll use minus here. And then speed plus or minus speed of the source. In this case, the source is not moving. So we have plus or minus 0, speed of sound plus or minus 0. So in that case, the plus or minus doesn't matter anyway, because plus or minus 0 is no change. So it looks like the multiplier here is going to be 343 minus 8 divided by 343. And note that the units of measurement here are meters per second in the numerator and meters per second in the denominator, so those are going to cancel out anyway. So 343 minus 8 is 335. Divide that by 343, and we get about 97.7%. So 500 hertz times 0.977, and that's going to be about 488. So that's the frequency you hear. If you're running away from the speaker mobile, then you hear a sound that is a little bit lower than the 500 hertz it's producing. You're going to hear a lower pitched note. And we can now say exactly what note you're going to hear. Any questions on that?
Casey, I just have a real quick question about determining the sign either of plus or minus.
Mm-hmm.
So you're always going to look first at kind of like maybe your picture or something to see how the frequency is changing, and that determines your plus or minus sign?
Yeah, I look at it in terms of conceptually, should this direction of motion, should I expect that to create a higher or lower frequency than the original? And then I look in terms of the equation and say, if I want the result to be smaller than the original, should I be multiplying by a larger or smaller denominator, numerator, and a larger or smaller denominator? So look at numerator and denominator individually.
Oh, okay, that makes sense.
In this case, only the listener is moving, so only the numerator needs to be cared about. So we just look at it in terms of, if we want where we're expecting a lower frequency heard, a lower observed frequency. So we want the result to be smaller than the original. A smaller numerator leads to a smaller result. So we want the numerator to be smaller, so we'll use subtraction.
Okay, that makes sense. Thank you.
Mm-hmm. Any other questions on this example? All right, let's try out one more example with a moving source and see what that looks like. So in this case, let's say you as the listener are standing still. So the listener is stationary. But let's say the source is moving. And let's say the source is moving towards you. So that's going to modify the waves. Let's say the car is still creating a 500 hertz noise. It's still the same speaker. But if it's moving towards you, what's going to happen to the forward moving wavefronts?
They'll compress.
Yeah, the forward moving wavefronts get compressed in space. They're going to be bunched up closer together. So forward, we're going to have wavefronts bunched up closer together. Behind, we're going to have wavefronts more spread out. So the wavefront diagram would look something like that. Instead of the circles being concentric, they're going to have different centers because the source is moving forward. So this wavefront was emitted from a point further forward than this wavefront was. They're no longer centered on the same point. So the waves in front get bunched up, the waves behind get more spread out, which means you should be hearing a higher or lower frequency. If the speaker mobile is moving towards you and the waves are getting more bunched up, would you expect, you'd expect a higher frequency. You're gonna be getting hit by more wavefronts per second. So you hear a higher frequency. You get hit by more wavefronts per second. Notice that also corresponds to a shorter wavelength because the waves are bunched up closer together in that direction. And let's say we know what you hear. Let's say you know that let's say we don't know the speed of the speaker mobile. You know the frequency it's producing is 500 hertz. And let's say you actually listen to the tone that you hear. You use an electronic musical instrument tuner to measure the frequency, and you find that the frequency you observe is measured to be, let's say, 520 hertz. So we've got the frequency created by the source, and let's say we experimentally measure the frequency heard by the observer. So if we list out everything we know here, we know the frequency of the source, 500 hertz. The frequency heard by the observer or measured by the observer, 520 hertz. What don't we know here? What's the missing information?
The velocity of the source.
Yeah, we don't know the speed of the source. We don't know how fast the speaker mobile is moving. So that's going to be our unknown that hopefully we'll be able to solve for. Do we know the speed of the observer?
0.
Yeah, if you're just standing still and listening, your speed as the observer is 0. And speed of sound we can still assume is the same standard 343 meters per second. So with all that information, we should be able to fill these in our Doppler effect equation and solve hopefully for speed of the source. Figure out how fast that speaker mobile is actually moving. So let's try filling that in. And since we're running out of space, I'm just going to fill it in this equation here. Although it might be more useful to solve for speed of the source algebraically with variables before we even fill in the numbers. One exception, I am going to fill in speed of the observer because that's 0. We know the speed of the observer is 0. Also, let's choose a plus or minus here. How would we decide on a plus or minus for the denominator?
Would it be a minus sign to make sure that the overall diffraction would increase for frequency?
Yeah, overall we want an increase. If the source is moving towards you, we're expecting to hear a higher frequency. In fact, we better get a higher frequency because that's the number we have here. So to make the result bigger, do we want the denominator to be bigger or smaller?
Smaller.
Yeah, a smaller denominator results in a bigger answer. So we want the denominator to be smaller than the numerator. So we should be expecting a subtraction here to make the denominator smaller and therefore make the result larger. So we're expecting subtraction. And let's see if we can solve that. We want to isolate speed of the source. So let's see if we can solve that algebraically and then plug in the numbers. So looks like we've got frequency of the observer, which we know, equals frequency of the source, which we know, times V over V minus V source. So V is speed of sound, which we know. V source is the only unknown. So without even plugging in any more numbers yet, how would you algebraically start isolating V source? What's the first thing you would want to get rid of?
Do we divide by the frequency of the source?
Yeah, let's try dividing both sides by frequency of the source. That at least gets rid of that extra multiplier. So frequency of the observer divided by frequency of the source, that ratio of frequencies, so that'll just be 520 over 500, equals the ratio of speeds, speed of sound over the difference in speed of sound minus speed of the source. We now have a slight problem that speed of the source, the variable we're trying to find, is in the denominator. How could we get that out of the denominator?
Cross multiply.
What was that?
Cross multiply.
We could, but there's actually a faster way. If the only problem here is you've got like a fraction equals a fraction, but the variable you're looking for is in the denominator, one operation will just flip the fraction upside down.
Like taking the inverse of both?
In a situation like this, where you've got a fraction equals a fraction, and the only difficulty is that the variable you want is in the denominator, I would just proceed by inverting both sides. Both sides to the -1 power. That just flips both fractions upside down. So this becomes frequency of the source in the numerator over frequency observed in the denominator. This becomes V minus V source over V, speed of sound. And now it becomes much more straightforward to isolate V source because it's in the numerator. At this point, what else do we need to do to isolate V source? How do you get rid of divided by V?
Multiply by V?
Yeah, if we just multiply both sides by V, and then what? Again, trying to isolate this part.
We would subtract V.
Yeah, if we subtract V from both sides, so that gives us negative V source equals V times this ratio of frequencies minus V. And then what's the last thing we need to do there?
Multiply by -1.
Yeah, if we just multiply both sides by -1, that changes the sign on everything. So we get V source equals, this one's positive, so I'm going to put that first, speed of sound minus speed of sound times frequency of the source over frequency of the observer. In fact, at this point, we could also go one step further algebraically. These terms both have V in them, so what can we do there?
Cancel them out.
We can't exactly cancel it out because we don't also have a times speed of sound over here. But in
Factor it
general,
out.
yeah, if the same variable shows up in all the terms on one side, we may as well factor that out. So speed of the source equals speed of sound times, in parentheses, 1 minus this fraction. And this is kind of convenient because it gives us the speed of the source as a speed of sound times some multiplier. So we can think of this as the speed of the source is some specific fraction of the speed of sound. Any questions on all the algebra we've got there so far? Before we actually try plugging in the numbers. So let's substitute those in and see what we get. At this point, we now have speed of the source equals speed of sound times 1 minus source, the frequency created by the source over frequency observed by the listener. Speed of sound is our usual 343 meters per second. And we got 1 minus frequency produced by the source, that's the 500 hertz. Frequency heard by the observer, that was the 520 hertz. And we can reduce this fraction, 500 over 520. We can cancel out a hertz. We can factor out a power of 10. 50 over 52, what does that reduce to? Those are both even, so we can divide them by 2, right? What is 50 over 52?
25 over 26?
Yeah, half of 50 is 25. Half of 52 is 26. And what's 1 minus 25/26?
One over 26?
Right, because 1 is 26 over 26. Subtract 25 over 26. We're left with 1 over 26. And this is a very convenient way to write it, because we can now say for certain that the speed of this speaker mobile is 1/26 of the speed of sound. And it's often very convenient to write speeds of moving objects as some fraction of the speed of sound. Partly because the speed of sound itself is a pretty important speed to be going. You get that fast and you get a sonic boom and extra weird sonic effects on your speed. But writing this as a fraction of the speed of sound tells us this is way slower than the speed of sound itself. Dividing that specifically, 1/26 of 343 is about 13.2 meters per second. So we now know exactly how fast the speaker mobile is traveling. Not by any specific measurement of its speed directly, but just by comparing the sound we know it's emitting versus the sound we actually hear and plugging all that information into the Doppler effect equation. And the nice thing about running these calculations, or running all the algebra before we plug in any numbers, instead of just getting one number, we now have a formula for the speed of the source, no matter what the source frequency and observer frequency are. So if you had to do several of these problems, if you wanted to say, well, what if the car is moving, but it's producing this other frequency and you're hearing this different frequency, you can just plug those numbers into the formula we just got without having to run the algebra all over again. Any questions on that use of the Doppler effect? Or any other questions?
I wasn't here for the very beginning. Sorry. I wasn't here for the very beginning, so I missed that part. Is V equals 343 meters per second a constant?
I don't know if I'd say it's exactly a constant because it does change to some extent, but it's a pretty standardized value for the speed of sound.
Okay.
And presumably that would be given. In general, the V in the Doppler effect equation is just the speed of the wave we're talking about. If we're talking about sound traveling in air, that's usually going to be about 343 meters per second. It varies to some extent with temperature, but I think 343 is the standardized value at, I think, 0 degrees Celsius and atmospheric pressure at sea level. So higher or hotter or colder temperatures are going to change that a little bit, but not very much. And other types of waves, of course, will have different speeds, or other medium as well. So for instance, sound in water or sound in steel are going to be much faster. Or light is going to be way, way, way faster. So it's just the V is supposed to be the speed of whatever type of wave we're talking about in the relevant medium. Any other questions on that? And then the more complicated case would be if both the source and the observer are moving. In that case, you would just combine the two effects. You'd be plugging in speed of the source and speed of the observer into the original equation and making decisions about plus or minus for the numerator and denominator individually, using the same sort of reasoning. Another complication that can sometimes show up is echoes. Like typically, if you're, like, let's say you're trying to measure the speed of a car using the Doppler effect, but you don't know what sound it's producing, or maybe it's not even producing a sound loud enough for you to hear easily. What you can use is a sonar gun, which creates a sound, shoots it towards the car, and then the car, what's going to happen when the sound hits the car?
Bounces back.
Right, it's going to bounce back. You get an echo. So when you're shooting the sound towards the car, you treat your sonar gun as the source and treat the car as the observer, and figure out what frequency the car hears. But then when it bounces back, you treat the car as the source and treat your sonar gun as the observer. So you'd be using the Doppler effect twice to figure out the speed of the car. But whatever you get is the frequency that the car observes in the first leg of the journey. The car is going to echo back that same frequency, and you treat that as frequency of the source in the second part. Any questions on that?
Casey, just real quick, you said for the echo, like if that was like a problem, basically the source and the observer like switch?
Yeah, exactly. Because the sound in the first part, the sound is traveling from the sonar gun towards the car. And then in the second part, the echo travels from the car back towards the sonar gun. So you the car is the observer in the first part and is the source in the second part.
Okay, thank you.
Mm-hmm. And the same is true for echolocation done by bats and dolphins, for instance. The bat emits a high-pitched cheep sound. The sound travels from the bat towards, let's say, a moth, and then hits the moth and bounces back. So on the way out, you treat the bat as the source and the moth as the observer. Figure out what frequency does the moth hear. And then for the bounce back, you treat the moth as the source, echoing back the same frequency it heard, and the bat as the observer, listening for that bounce back. And echolocation is really great in this regard. You can figure out, based on how much time it takes for the sound to go there and back, you can estimate how far away the moth is. And based on the frequency you hear, the pitch you hear, and how different that is from the pitch you emitted, you can estimate how fast the moth is moving and whether it's moving towards you or away from you. So you get a really complete picture of your surroundings just based on the sound you hear back. Any other questions on that?
Wait, sorry, Casey, I know you just repeated this, but for the echo thing, the gun is the source in the first part, and then the car is the source in the second part. Is that correct?
Right, because in the first part, the sonar gun is actually literally creating the sound. In the second part, the car isn't really creating a sound, but since the sound is bouncing off of the car, from the moment of the echo onwards, you can treat the sound as if it came from the car. Even though the car didn't create the sound, it just bounced off the car, you can still treat the car as the source after the bounce.
Okay, so in that case, like, would we set up two different like equations for that? So we would like solve for the speed or like whatever we're trying to solve for, and then would we have to do it again for the second part, or isn't it just the same answer since it would like reflect back with the same?
It would be so you have write out frequency of the source or frequency observed equals frequency of the source. And for simplicity, let's assume that the person holding the sonar gun isn't moving. So you're just standing here holding your sonar gun device, and there's this car that's moving. So we're treating the sonar gun as the source and the car as the observer. And this wave travels forward and hits the car. In that case, the source is not moving. We've got the car is moving, so we're going to have, and Remind me, was observer in the numerator?
Yeah.
Okay. So the observer, the car, is moving, but the source is not moving. So we're going to have v plus 0 here. So if we start labeling these, the observer is the car here. So this is the car. The source is the sonar gun. And the observer, again, is the car. So the frequency observed by the car equals the frequency produced by the sonar gun times speed of sound plus or minus speed of the car divided by speed of sound. And would we be using plus or minus here? How would we make that decision?
Minus, because the observer is moving away from the source.
Yeah, if the observer is moving away, we expect lower frequency, right?
Yeah.
Just like for the last time, it's taking more time for each wavefront to catch up. So we expect a lower frequency to be observed. Therefore, we should use subtraction in the numerator. So, and maybe you don't know all these. Like presumably you're using the sonar gun because you don't know the speed of the car. So the speed of the car is unknown, but frequency observed by the car is also unknown. It's not like you're going to call up somebody in the car and say, hey, can you remind me what sound you're hearing from this sonar gun? Instead, how do you get a signal back from this? How does the sonar gun, the detector part of it, get information about the car? You send out this sound wave, and then what?
Does it bounce off of the car back to the gun?
The echo bounces off the car and returns to the detector part of the sonar gun. So on the way out, your equation looks like this. Then on the way back, you're going to get a different equation. On the way back, we're going to have, so let me just write out, actually, let me use a different color here. It means that can be very visible. If we write out the exact same Doppler equation, for our frequency of the observer equals frequency of the source times speed of sound plus or minus speed of the observer divided by speed of sound plus or minus speed of the source. In this case, what are we treating as the source?
The car?
If we now have the wave, the echo, bouncing back from the car towards the detector part of the radar gun. Where is this sound coming from? On the way back, we're treating the sound as coming from where?
The car?
The car.
The bounce back is coming from the car itself. So we're going to treat the car as the source, and we're going to treat at least the detector part of the radar gun as the observer. Because the radar gun consists of the actual sound producer and also a detector that picks up the bounce back. So everywhere we see source, we're going to replace it with the car. And everywhere we see observer, we're going to replace that with the detector. The detector isn't moving. You're just standing there pointing the radar gun or sonar gun and detector at the car. So speed of the observer is going to be 0. And then frequency of the observer, I'm going to write frequency at the detector here. Because that's the detector portion of the sonar gun. It's what you actually observe, what you measure. And note that that's not going to be the same as the frequency produced by the sonar gun in the first place. You hear back a different sound than the sound you emitted. And then this V plus or minus 0 is just going to be V. And we still need to decide about plus versus minus in the denominator. The car, the source is moving away from you. Would you expect that to make these sound waves hit you more frequently or less frequently? If the source is moving away from you, would you expect those sound waves to be more bunched up or more spread out?
More spread out.
More spread out. And if the sound waves are further apart, would they be hitting you more times per second or less times per second?
Less times per second.
Yeah, less times per second. So that's going to be a lower frequency. You're going to be hearing a lower frequency than the frequency the car is emitting or bouncing. Because if the car is moving away from you, like let's say one wave hits the car and bounces back and takes a certain amount of time to get back to you. By the time the next wave shows up, the car has moved a little further away. This next bounce back has to travel further to get back to you. Since it's traveling further, it's going to take a little bit longer than the last one. Each wave takes a little bit longer, a little bit longer, a little bit longer than the last one. So it's going to be less and less frequent. You're going to get fewer cycles per second received. We should expect a lower result. So should we expect the denominator to be large or small?
We expect a bigger denominator.
Yeah, a bigger denominator is going to lead to a smaller result, which is what we want. So we should be using plus here. Speed of sound plus speed of the car. So we now have two equations linking frequency that you create with a sonar gun and frequency received by the car, and another equation linking frequency bouncing off the car and frequency received by the detector part. How could we combine these equations together? What do these equations have in common?
The V car.
It's the same V car, and presumably that's the unknown we're trying to find. And what else do they have in common?
V.
They've got the same speed of sound, although we know the speed of sound. That's just a number, presumably 343, that we could plug in. Is there another unknown that they have in common?
Velocity of the car?
So we've got the same velocity of the car, which we don't know. What else, though? What other variable shows up in both of them?
Is it the frequency of the car?
Yeah, this frequency of the car, because this is supposed to mean the frequency the car receives from the sound wave traveling towards it. This is supposed to represent the frequency of the echo bouncing back off the car. But those are the same frequency. It bounces back the same frequency that it receives, which means we can use a substitution. This formula for frequency heard by the car can be substituted into this frequency of the echo bouncing back from the car. So combining those together, we get frequency of the detector, or frequency heard by the detector, equals frequency heard by the car, which is this whole thing, so this whole thing is F car that we're plugging in here, times this fraction. At that point, the times V and divided by V cancel out. So frequency heard by the detector, and that is presumably known because that's going to show up on your display panel on the sonar gun, equals frequency created by the sonar gun, and we know what that is, times this ratio, speed of sound minus speed of the car, divided by speed of sound plus speed of the car. So now frequency created by the sonar gun is going to be a known value. Frequency received by the detector is going to be a known value because that can be measured by the detector. Speed of sound is known, that's 343 meters per second. Speed of the car is the only unknown left, so we can then solve for that. And the algebra is going to be a little complicated because we've got the unknown variable in numerator and denominator, But how could you just get rid of this denominator entirely? What's the opposite of dividing by something?
Multiplying v plus v car to the other side.
Exactly. Multiply both sides by this whole thing, v plus v car, and you get frequency detected multiplied by v plus v car equals frequency of the sonar gun times v minus v car. Distribute the frequencies to both of these. Move everything with a v car in it to one side. Move everything without a v car in it to the other side. Combine like terms. You should end up with just v car times something equals a number. Divide by that something and you know the speed of the car. So the algebra is a little trickier, but it's the same process each time, and you should end up with just a formula, speed of the car equals some formula. And you can just program that formula into the computer chip in the radar gun or sonar gun so that the sonar gun just knows the frequency it's creating, measures the frequency that's bouncing back. The computer plugs that into the formula here and outputs on the display panel how fast the car is traveling. Any questions on that? All right, sounds good. Have a good weekend, and I will see you next time.
Thank you, Casey.
You're welcome.
Yeah.
Bye-bye.